Welcome to the channel. In this problem, the square wave input is applied at the inverting terminal of the operational amplifier and we have to predict the output. I am drawing the same circuit. This is inverting terminal, input capacitor, feedback resistance. This is output voltage. Positive terminal is connected to ground and the square wave input at the inverting terminal. So this is capacitor C, feedback is R, feedback resistor is R. In this case, we are getting output voltage which is equal to, I am considering the I current is flowing, input which is applied at inverting terminal, so 180-degree phase shift, so minus R into I, but I is the current which is flowing through the capacitor, so what I am getting, R into C dVi by dt. Current flowing through the capacitor is nothing but capacitor into dVi by dt input voltage, which is in differential form. So this type of circuit is nothing but differentiator. But this is a practical differentiator. This type of circuit is nothing but the differentiator. But this is ideal differentiator. But the differentiator in practical form, which is more applicable. So in this case, practical differentiator, we are taking one resistance is in series with capacitor. This is inverting, this is non-inverting terminal. And we are taking resistance, say this is feedback resistance. This is in parallel with again one more feedback capacitor connected to the output. And this is output voltage V0. Say this is R1, say this is C1. Here the input voltage Vi. So this circuit is more practical. Thing is that we are taking one pole in the equation. This is at RC. If you consider the response, say this is gain, this is frequency, this is ideal response. Practically we are taking this response, and this is response is practical response. So by adding one pole, which means that by taking one resistance in series with capacitor and one capacitor in the feedback which is in parallel with resistor, we are going to add one pole. Omega is equal to 1 by RC, and the response will be coming down practically, since if this is gain response and this is phase response, we know that this is gain crossover frequency omega GC and this is phase crossover frequency omega PC. In order to make the system more stable, gain crossover frequency must be earlier than phase crossover frequency to ensure the stability of the system. So by adding one pole to this practical, I mean to say to this ideal differentiator, we are ensuring the stability of differentiator, and hence we are saying it is like a practical differentiator. Coming to the solution of this problem, the square wave input is given. So differentiating input, this is input. So output waveform will be, let's see the output waveform. The input is applied at the negative terminal of the operational amplifier, I mean to say inverting terminal of the amplifier. So if square wave, during negative square wave, initial capacitor charges to the positive peak side. Capacitor charges to the positive peak side and immediately discharges to the feedback resistance. And during positive, we are getting the negative spikes and immediately discharges to the feedback resistor. Again for negative, we are getting the positive spikes and immediately discharges. And again for the positive, we are getting the negative spikes and immediately discharges to the capacitor. So it depends upon the RC time constant. So we are getting the positive spikes during negative square wave, and during positive square wave, we are getting negative spikes. This will be the nature of the output waveform. If the input is square wave, at the inverting terminal, output will be in spikes form. So this is the solution of this problem. Thank you.